So, good morning, ladies and gentlemen. I congratulate you on so many showing up after a banquet. I know, particularly on a Sunday, so clearly you are keen. And so I'm going to try and give you a bit of a background on the ExoMars project. Dr. Zubin did a very good job of giving the summary, almost to the point where perhaps I could even sit down, but I won't. I'll try and consume my 30 minutes. ExoMars is a cooperation between European Space Agency and the Russian Roscosmos state enterprise. It's a very big cooperation, and I'll show you some details of it a little bit later. Let's start at the beginning, shall we? Aurora, the Aurora program of the European Space Agency. It was actually born around 2001. The agency and the European governments had a desire to try and have a program of concerted exploration of the solar system, so that Mars, the Moon, but actually the further bodies as well. And that was started in 2001. Several studies were established, and a program of technology development was begun such that a program could be built up. It was early days, of course, small budgets, but studies were set up in that period of time to try and establish, in particular technologies, and with a very key point, looking for signs of life. But also there was a linkage to eventually how one would use all the knowledge for future human exploration. It's not called up specifically there, but it's actually the last bullet. So ExoMars eventually got approved in 2005. At that time, it was a fairly small mission. But it was set up to develop the technologies, particularly for landing on Mars, and in fact to start the search for life with a rover. Well, today we have a very broad cooperation. 2 missions. 2016 launch, of course, happened this year. 220 launch will happen in July 2020. And you can see from the pictogram, aside from anybody who might read some Cyrillic, you can check the translations if you like. It actually is a cooperation where the Russians are bringing their launchers, a very big, powerful launcher, 2 of them, in fact. And as well as that, they're building a descent module for the 2020 mission to put an ESA rover on the surface. They will also have a surface platform, which they'll use for science once the rover egresses from the platform. They've also provided some science instruments on the TGO, and I'll show you a little bit later that. On the left-hand side, you can see actually the spacecraft, which is flying now, is mounted on top of the upper stage, the Breeze upper stage, and that's a process just before actually getting ready to be encapsulated and going for launch. Well, there are very clear mission objectives. The ExoMars program has a whole series of them. And when we had a first mission, originally all the objectives were set up for the same mission. With time, that evolved actually into the 2 missions. In fact, the 16 mission has very particularly a science objective on the level of the orbiter, and a very primary technology objective for the lander, the Schiaparelli. This technology objective is actually the first step of the Aurora program in a concrete manner to develop the technologies in Europe to land on the surface of Mars, potentially other places in the future. Some elements of it could be used. And so that is actually a spacecraft which will be entering the atmosphere on the 19th of October, while the TGO is entering the orbit. On the science side, there's a nice little picture of the Mars Express satellite, which is ESA satellite. That satellite was using some instruments, some infrared instruments which identified possibilities of some methane around Mars, and actually was tracking it to some degree. Based on that, there was an interest which grew on the trace gases of Mars. And coming out of that, in fact, this mission will have a series of instruments which will be dedicated to mapping the trace gases around Mars. And there's a series of infrared spectrometers, a camera, and various other instruments. One very important objective also for establishing the exploration program around Mars for Europe was the establishment of a communications link, and that's the bottom programmatic objective. So this orbiter will also have the job of maintaining a relay link to any surface assets, rovers, surface platforms, or anything else. And in fact, it's already in the planning stages to certainly support this mission, the landing of this mission, but other missions with NASA or anybody else who happens to come along at that time. I'd like to just very briefly give you the summary of the mission. It's a very particular architecture, the 2016 mission. We launched with one spacecraft. As we approach Mars on the 16th of October, we'll split into two separate spacecraft. One will land and the other one will go into orbit. Most missions don't do this. There's a certain degree of criticality as you approach the planet. Certain things have to happen, or you can have some very nasty consequences. So at 3 days before arrival, we have to separate the Schiaparelli from the TGO. Shortly thereafter, we need to make a maneuver from the TGO to deflect it away from the planet, because everything's on a collision course right now. If you want to land, it makes sense you actually have to collide with the planet in some strange way. And then in parallel, both will be doing their operations, and the TGO will be listening to the Schiaparelli, picking up the radio signals as it's landing. Well, to do that, this particular satellite, which is quite a large satellite, I'll show you some pictures a little later on, has to do quite a few functions. It has to carry this payload. You can call it a payload, but it's actually a separate mission. That's the Schiaparelli. It has to perform the scientific measurements once it reaches its science orbit, and it has to actually do that by employing an aerobraking technique. So it's a satellite which has a lot of functions to do, and all of that requires quite a bit of propulsion. 60% of the satellite is actually propulsion. We have the problem of the communications. As you know, Mars is a little bit away. You can have quite long durations for communications, so you send a command. Right now, where we are today, it's about a 10-minute lag. You send a command, you wait 10 minutes for it to get to the spacecraft. Confirmation comes back 10 minutes later. So if you have a lot of interaction necessary, for example, in an urgent safe mode or something like that, it takes quite some time to recover. If it's all automated on board and is running according to timelines or other cues, then of course the satellite proceeds and does its operations. We have something we call the fail-ops mode. Fail-ops meaning that you give the satellite the set of instructions for operations, and even if it has a failure on board, it will reconfigure the satellite to continue those operations. This is particularly key in the aerobraking mode. After we achieve the orbit around Mars, the satellite goes into a highly eccentric orbit for the capture. It reduces the amount of fuel you have to use. And because we won't have enough fuel to get down to the science orbit, we'll be employing aerobraking. We've never really done that in Europe. We've tried to test it on another satellite called Venus Express, and we actually did a few dips into the atmosphere of Venus and found the methodology, if you like. But of course, the atmosphere of Venus is quite different than Mars, et cetera, et cetera. So this is the first time we'll really be doing it for a real operational objective, and that is to get the satellite down towards the operational orbit of about 400 kilometers circular. Even with that, at the end, you don't gain much by dipping into the atmosphere. So each time you go near the pericenter, you dip into the atmosphere, and that brings down the apocenter. When you get down fairly well down in the apocenter, of course, it's not very efficient. So sooner or later, you have to use some fuel to circularize. In the end, we'll end up using about a year's time to get down to the orbit that we want to finally circularize. And so 2017 will be devoted to that once we're in orbit. Well, a quick picture of the orbiter. There's the 4 instruments on board I was mentioning. They come from 2 from Europe, 2 from Russia. We have the camera, which is the Swiss contribution. The infrared spectrometers are a Belgian contribution, and the 2 Russian instruments are an infrared spectrometer and the neutron detector. On the far left, you see 2 white items. Those are the UHF antennas for the communications. And even though we still have a very broad cooperation with the Russians, NASA has maintained an interest and a cooperation, which is good. So they've actually provided the UHF radio transceiver and those antennas. So we have a nice international satellite there, most interesting combination. Well, finally, maybe a real picture. So far, it's all been nice computer-generated images. On the top left, gives you some of the dimensions. It's about 17 meters across, so it's probably about half the hull here. It certainly would stand as high as the ducts in the back, because it's quite a large satellite. It's about 4 meters. Carrying, the mass is about 4.3 tons, a little bit over. And as I mentioned, 60% of that is fuel. Even that's, of course, not enough. That's why we have to do the aerobraking. But as it turns out, and it certainly wasn't the criteria or objective, it turns out we are sending the biggest satellite ever to Mars, at least from the launch point of view. And so it's nice to be in the record books for a little while, but I look forward to the next step where somebody sends something very big, and perhaps with humans on board. So I've put together a little collage, if you like, just to give you a sense of what's happened. We moved to Baikonur just before Christmas last year, and spent about 3 months putting together our satellite. It actually took 3 Antonov aircraft to move us into Baikonur. We had enormous amounts of equipment, and that's not even personnel, that's just the equipment. So actually it was 2 spacecraft plus all the support equipment. And during the course of Christmas, etc., we put all this together. So it was a very intensive campaign. We had to launch on the 14th of March. You can see, and in parallel, of course, our Russian colleagues were putting together the rocket. The payload actually is up on the little gray part on the rocket that's slightly tilted up. Right now it's covered with a thermal cover in that photograph. But that's where the spacecraft is, and it's part of an upper stage of 22 tons. That photograph is with the spacecraft being tilted up, the entire rocket, because that's the technology the Russians use for their rockets. Everything is done vertically, horizontally, and then tilted up vertically. And once we were on the launch pad, after a few days, we took off on exactly the time of 9:32:41, so 9:32 minutes and 41 seconds. And that was Zulu time. And it's interesting with the Russian launchers, this is defined very far in advance, and that's when you launch. If you don't launch on that second, you don't launch. And so they're very precise in that sense. The rocket itself is quite an impressive machine. It weighs something like 700 tons, and it has about a 1,000-ton propulsion at the time of that launch. And so it really does take off like a rocket. It has a nice ratio of thrust to mass. In 9 minutes, you're in orbit around Earth, and then that's the 3 stages expanded, and the upper stage spends the next 11 hours actually to build up the orbits until finally injection into interplanetary trajectory. At the point on the picture on the top left, that's the point where the separation occurs. That's roughly 12 hours after launch. And at that time, for this mission, this rocket had put us spot on the trajectory. It was actually a beautifully nominal launch, and so a very good job on the Russian side. Well, I've got a nice little trajectory. It's not very exciting, but it's maybe interesting for a quick look. So from there, we're in a kind of a normal trajectory across to Mars. It looks like it's a straight run, but it's not, of course. We've had several corrections of the trajectory. 1 or 2 were done in the July-August timeframe. One was about 350 meters per second, and that actually puts the system on a collision course towards Mars. And from there, you start adjusting and getting closer and more precise. Last week, I think it was Thursday, we did the trajectory correction maneuver, which is down to the order of millimeters per second. And that's quite impressive. We're even talking about doing a further one, but it's probably not necessary. So if you consider that that's a relative speed of 3.5 kilometers per second, we're trying to measure velocity at millimeters per second. It's quite impressive with the techniques for navigation through delta door and things like that. So it's 1 part in a million. Well, let me try and do this again. I'm going to try and catch the moment today, if I can. Whoop. Well, I passed it. So we're within 7-8 million kilometers, and we're ahead of the planet now. So in fact, the planet's catching up to us, and we're getting ready to do these critical operations in 24 days. 24 days we'll be landing on the surface of Mars. 3 days before that, we'll be separating. Exciting times. Well, the Schiaparelli, the technology demonstrator, is a first for us in many ways. We've had to develop the parachute technology, so we have a supersonic parachute of 12 meters. The thermal protection system we've beefed up to actually deal with a dust storm, because of course we're arriving approximately the dust storm season, so basically we've put on more mass should there be an abrasion. We have other items such as the radar, which has been basically developed from the basic requirements of the mission, and so we have that in hand now, and it will be used on the future missions as well. Much of this will actually go forward to the future missions, and that's actually why we're doing this mission. So there is a linkage between it, and that's why it's a technology demonstrator for us. Sorry for that. We'll also have a series of sensors which usually don't end up on planetary probes, so we'll be able to characterize the aerothermodynamic environment around the probe during the entry. This will help possibly for future re-entry designs, and all of that will land on top of a crushable structure, which is interesting. We looked at airbags at a certain time because they have been used with success several times, and at a certain mass ratio, you're just as well to just drop on the surface of the planet and crush something as you are to have a bag which crushes, and that's the choice we made. So another quick little video. Now what you'll see basically is in the top left-hand corner, but of course you can't see it. So I'll try and call it out for you. It's a simulation of what's going to happen on October 19th with the probe. So it starts at about 121 kilometers, 21,000 kilometers per hour, and that's the entry phase where things get nice and warm, atmosphere gets exercise for a rapid slowdown, and this is the peak heating and slowdown accelerations. Once it goes through that, we're at about 45 kilometers and traveling about 19,000 kilometers per hour. And then we go through the period of the parachute, which is deployed shortly thereafter. We're down around 11 kilometers there. Roughly, it's a supersonic deployment, so it's 1,700 kilometers per hour. And once we get down to about the 7-kilometer mark, the front shield comes off, the radar becomes active, starts sensing the surface, parachute verticalizes the system, and it continues to go down to about 1.2 kilometers, where in fact the back shield comes off and powered propulsion takes over. So from that point on, it's about 350 kilometers per hour, and that terminal phase is powered with the rockets, such that it gets down to about the 2-meter altitude, and the rockets cut off, dropping at a speed of about 4 kilometers per hour. And this is where the crushable material comes in. Essentially, the last little bit is just dropping onto the surface. You get a nice crushing effect. So of course, certain size of stones and things like this are factored into the equation. Well, once on the surface, it won't last so long. It was a technology demonstrator, and it's powered by batteries. But we did put in some science to try and get some advantage out of the possibility for the batteries, whatever's left in it. And we have a package called DREAM. So they'll be doing some atmospheric science, and they have a very special sensor called the micro-Aries, which will be looking for electric fields to do something about detecting any electric fields which could have effects on dust storm pickups. Finally, once it's all finished, there will be a laser reflectometer in the right in the middle in the left-hand corner. It'll be there for anybody who will be doing any kind of studies in the future with orbiters, or possibly somebody who has a laser from Earth one day that can actually reflect it off the surface. So it'll always have a purpose and a sense up there. Well, I've spent quite a bit of time on the 16 mission because that's the moment for us. We also have a 2020 mission. I won't spend too much time. However, the objectives are extremely important. It's the search of life, and it's the use of all the technology to actually put our rover on the surface, where we spent quite a bit of energy. So I'll go through these slides fairly quickly. This is the configuration. It will be a different configuration. We'll go straight into the entry as a typical lander does, so we won't have an orbiter. We'll use the orbiter that's in place already. That's, again, the link between the two missions. Once on the surface, the rover will egress. A landing platform will stay on the surface, which will be the Russian element for science, and the rover will be operating for the European science through a center in Italy, in the so-called ROC. One item which is of interest to many people is the drill. We have a drill in our hands right now, which does the drilling down to 2 meters. We've done many tests on simulated Mars atmosphere, the temperatures of Mars, including ice and all the characteristics that one would fear if one was going to take a sample. So we can go down 2 meters, pick a sample, put it into the rover. And one of the reasons for going down 2 meters is, in fact, the concern of oxidation at the surface. So UV radiation penetrates a millimeter. You can have oxidants down to 1 meter. And ionizing radiation can even penetrate down to 1.5 meters. So that little cartoon, if you like, shows the reason the 2-meter drill is so important, particularly for the search for life, because it gets underneath the oxidized layers. Some of the instruments, we have a whole range of instruments, and again, NASA's involved in one of them. This is the contribution on the 2020 mission. And maybe a word on the international cooperation, which I think is also very important to you, those of you who are interested in the Mars Society and the objectives of it. This slide is very oriented towards the classic spacefaring nations plus ESA, and it's based on the cooperation that we're involved in. And there's a growing pace of activities going towards a sample return. The Russians are thinking about another Phobos grunt mission, and of course the Aurora program in ESA is looking forward to further exploration missions in the future. Just Mars. We haven't considered all the other players, interested parties these days, such as Emirates, who are sending a mission, the commercial interests that are trying to have missions to Mars. So if one puts it all together, in fact, this chart gets quite busy. And it's clear there's a growing interest and movement towards Mars. I don't talk about the moon, which is another chart, but the agencies also have quite some interest in that as well. Well, one last point. In any case, we are cooperating on the international basis because we have agreed rules for protecting Mars. Love them or hate them, it's for the future, and anybody who goes in the future should be able to have a planet which is not too contaminated, because it's impossible to keep it completely uncontaminated. I'm proud to say that we have respected these rules on this mission that will land on Mars, Category 4A for the COSPAR rules, and we're even below the bioburden requirements. Well, that's a fast run through the ExoMars program. 19th of October, I welcome you to check the website and explore around and try and get to know ESA a bit more. So thank you very much. Okay, so a little bit of time for questions. Yes. Please.
You said that the orbiter was supposed to look at the sources of trace gases. Given the difficulty of characterizing the organic and anorganic origins of methane, where are we with respect to the ability to do that remotely? And do you or are you talking about just geographically?
Yeah, I'm talking particularly geographically. So it'll be mapping the presence of the methane and trying to follow its evolution. Whether that can lead to understanding the real source is a step beyond that, in fact. So the actual determination whether it's biological or geological isn't specifically coming out of the data of the TGO. It's more of a mapping and characterization.
The size and mass of the lander is quite impressive. It compares with a Viking lander. But what's the main reason for landing an empty truck on the surface? It's just a few instruments.
I'm sorry, I didn't quite catch you.
What's the reason for the very few instruments on the lander? It's quite empty.
Yes, so why not more science instruments on the lander? The lander actually is a technology demonstrator. Its real mission is actually to demonstrate all the technologies to arrive on the surface of Mars in a complete state, sending data back to the TGO and any other orbiters. Actually, I didn't mention we have 2 NASA orbiters, our own Mars Express, the TGO, a radio telescope on Earth, all monitoring this activity. And that's the real objective of the lander. There was nevertheless an opportunity to put some science on, and it's limited by the mass and the power capacity of the technology demonstrator, and that's why it has that limit.
My question is this. Most Americans consider Russians are incompetent in space. So why are you working with them, and how competent do you feel the Russians are?
Well, I can only answer by saying they put us on our way to Mars spot on. Indeed, there was always the question, well, you're going to put all that hardware on a launcher, given the fact that they had had some failures. That was a discussion point. The Russian colleagues showed us their solutions for their problems and cooperated with us to understand how they were going to solve the problems. And I think they did very well, in fact. I think in the launching business, you can have a problem at any time, as we all know. That's the launcher side. On the technology side, they, of course, were very prominent in the exploration at some point in time. It's true, recently they had some bad results, the Phobos Grunt, for example. In fact, we're building a cooperation that works on the strong points of both sides. We are actually, some of the technologies that are used for the landing will be incorporated into the descent module to ensure the rover success on the surface of Mars. They have strengths in other areas. Their history on the landing capsules and those sorts of things will be melded with the success that we have on this technology. And so it's a cooperation in that sense. So we're quite comfortable with it, actually.
For the land or the rover, we all had a debate here that talked about, not being able to send the current rover to certain areas because of contamination. Do you know that you can go anywhere on Mars and not be restricted by that? That you all will be able to really go and do the research that you really want to go do and not have anybody inhibit you for those reasons? Thank you.
Well, we are going to try and be good citizens. Now, that doesn't mean you shouldn't question things, right? We are building the rover to look for biological signs. It's the so-called Class 4B of the COSPAR rules. But indeed, scientists might find areas that are more interesting. Unfortunately, often the places that are more interesting are also quite difficult in terms of the geology for actually roving around. If there was a site that was very interesting, so this so-called Class 5, and we could achieve the landing and rove, then I think probably the world would have to discuss, is it worth having a waiver for these rules? I think the scientific community would be open to it. But right now, we're building it based on following the rules, and we have many scientists who are involved in the research of Mars, participating in the selection of the landing sites. We haven't finalized our selection. We still have three sites open.
Just two quick questions. One, is there a camera on your Schiaparelli lander so you can get a picture of Mars? And second, is the rover payload in 2020 going to use a crushable terminal descent as well?
So the first question was, is there a camera on Schiaparelli? Yes, there is. It's a fairly basic camera, so it'll give us basic pictures as we're landing, so we will get some images. The second question was, will we use the crushable structure for the second mission, the 2020 mission? No, in fact, the crushable structure has a limit in terms of the mass that's useful, and the second mission, the entry is about 2 tons, and the actual landing mass is several hundred kilos, so it's beyond the crushable technology paradigm, if you like. You could do it, but then your accelerations are too high. So we're actually using legs and a throttleable engine, and that's actually a Russian technology that will be used.
So, hi. We're a few Canadians from McGill University in Montreal, Canada, and we heard that the drive system of the rover was designed, I think, in Canada. Do you have any update on the Canadian progress on this side?
Yes, so in fact it's MDA who does the chassis, we call it the BEMA for whatever reason, it's the bogie and electrical mechanical assembly. We've actually received shipment of some of the wheels, which I was telling my colleagues, my friends. The wheels are most interesting. They're actually not round. They're a little bit oval, but that actually happens to be an optimum for the particular design they're using. So we have some engineering and EQM models of the wheels, and the actual bogie system, the actual suspension, is in build right now for the EQM.
Hi, how do you see ESA being involved with human missions to Mars?
So the Aurora program, in fact, has as part of its objective to look in a very long path towards human presence. And part of the characterization of the Mars environment is oriented towards, for example, what kind of radiation is there, what kind of environment would humans be subjected to. So it is in the program. Now, implementing it is probably a longer-term story, but it is part of the overall ethos of the agency, if you like.
Hi, just a quick question. What kind of propulsion system will you be using for those micro-corrections on the Mars trajectory?
Yeah, we have a bipropellant system, so the larger corrections are using the bipropellant. And for the very small corrections, we'll probably use the thrusters. We have 14 Newton thrusters on board, which will be just pulsed.
Thank you. Very quickly, Antonio Gomez from Mexico. I would simply like to give you a recognition, give ESA a recognition on the Philae and the Rosetta missions.
Thank you. My colleagues would appreciate that. Thank you very much.
For the orbiter, does it matter the relationship in space between your orbiter and the orbiters already in orbit? Do you try to position it specifically in a way relative to where the other orbiters are? And if you do, how do you do that?
So our orbit actually will be about a 400-kilometer orbit. And indeed, there is an interplay between the existing orbiters. In fact, there's actually a working group established to coordinate all the assets around Mars for relay operations. Our orbit will be chosen particularly for servicing the ESA orbiter, but it also happens to be a convenient orbit for servicing NASA orbiters and also eventually servicing the landing platform on the Russian side. I think, so the 400 circular orbit is a nice orbit for communications and science, and I guess we will check that we're not in exactly the same orbit, but the likelihood is very small. It is, it's a big place just the same. Yeah. But there is a coordinating group between ESA, NASA, and actually Roscosmos is involved as well.
My question was that it came out here the other night that all other obstacles aside, the U.S. probably could not do a human mission to Mars due to planetary protection issues. How is the European Space Agency positioned on that? Are they in a similar situation where you couldn't land humans on Mars because you would violate planetary protection?
It's an interesting question. The planetary protection the rules are set up basically assuming there are future missions which need access to areas that are not contaminated. I think it's really a world movement that would need to be converging in the dimension of the COSPAR to discuss this sort of thing. It could be that when the sufficient resources and willpower of the world is such that we send somebody to Mars, it could be that it's also wise not to block them going somewhere because of planetary protection. It could be that area would be an omission of the planetary protection rules. And I think that kind of discussion would certainly happen before such a mission. So right now it's about sending robots, trying to keep it as clean as possible, and I think it's probably a wise approach for those great moments in the future. But it'll be quite a discussion, I'm sure.
Thank you very much.
Thank you.